we've got a fantastic panel here. We have Professor Jeff Hinton, whose name you've heard throughout the course of the morning. We also have Russ Salakudinov, who is heading over to teach for bright young minds at Carnegie Mellon after his stint here at the University of Toronto. And we have Ilya Sutskever, who was at Google until recently, and now he's the research director for the Open AI non-profit, which is set up to advance the pace of artificial intelligence research and do so in an open format. This morning we heard about how computers are learning to perceive the world, they're learning to understand images and understand audio. Now we're going to have an hour where we'll learn about what comes next, which is about inference and reasoning and memory and all of the things which make us, well, us. So with that, I'll let Jeff Hinton begin with his presentation.
Okay, I'd like to start by... echoing a previous speaker. There's nothing better than seeing your former students doing well. Okay. I'm actually going to give an academic lecture. I'm not going to mention verticals or horizontals or late-stage valuations. I'm going to tell you how neural networks actually work. So, in the brain there's real neurons, and we have artificial neurons, which are gross simplifications, but they're good enough to get the job done. And so if you look on the left there, there's a little picture of an artificial neuron that has one output. It gets a bunch of inputs from other neurons, and on each input it has a weight that it can adjust. And the way it decides how much output to give is it takes the inputs from other neurons, multiplies them by those weights, gets a total sum of input, and then gives an output that's that function on the right. So if it doesn't get much input, it gives no output. If it gets enough input, it starts giving an output that's a linear function of how much input it got. That's how a neuron works. And real neurons are more complicated, but this is good enough so we can study how big collections of neurons can do things. For example, we can study how a big collection of neurons might be able to take the intensity values in an image and convert those into a string of words describing an image. We hook up these neurons into networks. The simplest kind of network is a feed-forward network, where we have multiple layers of what are called hidden neurons between the input and the output. And so you put in some activities at the input, like pixel intensities, and you get out activities of some output neurons which might represent the classes of the objects in the image. And what we'd like this network to do is to take a bunch of pixels like that, and remember that's just a million triples of numbers that describe RGB intensities, and convert it into a string of words. So I want you to think for a minute what it would be like to write the program that does that. Okay, that was painful. You've no idea how to write the program that does it, so we need to get a learning algorithm to do it for us. And so we're going to have a learning algorithm, and I'm going to explain to you the learning algorithm we don't use, because it's one you can understand, and then I'm going to explain to you that the learning algorithm we do use is just an efficient version of this one we don't use. So imagine that you took a network that took input and gave you outputs, and they weren't the outputs you wanted. And how would you make it better? Well, what you would do is you'd take a random batch of examples, you'd give it the inputs, you'd look at the outputs you got, and then you change one of the weights in the network, just one of them. And you give it the same examples again, and see if the outputs were slightly better or slightly worse. And if they were slightly better, you keep that change. And clearly, if you did that for long enough, for evolutionary time, you could eventually find a bunch of weights that did a good job. But it would be very, very slow, particularly since you've got about 10 to the 14 of these weights you need to adjust. So there's a better way to do it, which is to use calculus. And the backpropagation algorithm is just doing what I just said, but it figures out for all the weights at the same time whether you should increase them a little bit or decrease them a little bit, so that on that little batch of cases you took, the answers get better. And so you take a little batch of cases, you'll figure out for all the weights in parallel how to change them, you then change them all a little bit in the direction that makes things better, and hey, eventually the thing will learn to do good things. Now, this has been used a lot since the 1980s. And so the backpropagation algorithm takes inputs, it runs through multiple hidden layers, it gives outputs, and then you send information backwards through the network, that's the calculus bit, to figure out how to change all these weights. And the thing we hoped is that if you show it images of animals, for example, and you tell it it has to classify them into birds or cats, then what it'll do is in the first layer of units, it will find things like edges. In the second layer, it'll find things like little combination of edges, maybe a beak or maybe a little bunch of edges that form a circle. And then if it finds the right combinations of beaks and eyes, then in the third layer, it'll say bird. And this is a gross simplification, but actually this now works. You can feed it lots of images and it will find features in the first layer that are simple features, and features in the second layer that are more complicated features, and so on until it's found very complicated features that are enough for it to classify. So backpropagation got people very excited in the 1980s when people first started running it on workstations. It was used for things like reading the numerical amount on checks at the end of the 80s, detecting credit card fraud, interpreting pap smears, but there was a backpropagation winter. It didn't work as well as its advocates thought it should work. So people like me went around saying, this is going to solve everything. We're going to be able to do speech recognition, we're going to be able to do vision, we're going to be able to do language eventually. This is amazing, and we will solve everything by learning these layers of representation. And we couldn't. So that was the end of that. Now, between about 2000 and 2015, there have been a bunch of little technical developments, like using different kinds of neurons, ways of preventing them from fitting the quirks of the training set. But all of those aren't the main message today. The main message is this algorithm, if you give it a lot of labeled data and you give it a lot of compute power, will do amazing things. And what was wrong in the 80s was simply we didn't have enough data and we didn't have enough compute power. We have made it work better with little technical advances, but those were the main things that were wrong. So the first killer app of the recent wave of interest in deep learning was for speech recognition, where people had a lot of labeled data. And on a relatively small data set with only a few million examples, 2 students in my lab, while I was away for the summer, trained a net that was deeper than I thought you should use, and it actually had 8 layers. I could only bother to draw 4. And they showed that they could slightly beat the state of the art on this small data set. And a very intuitive researcher at Microsoft called Li Deng then realized, well, if students in my lab could beat the state of the art, real speech researchers could do a lot better. And very quickly, this same network was used at Microsoft to do big vocabulary recognition and significantly beat the state of the art. So all the leading groups then got into this technology. By 2012, it was actually being used in the Android, in the cloud, if you had the Android operating system, for doing speech recognition for voice search in Google, and it gave a big decrease in word error rate. So I think Google were the first to get it into production. And now all of the best speech recognition systems use some form of backpropagation for training. The next killer app was object recognition. So until quite recently, people tried to do object recognition with training sets that were much too small. And someone called Fei-Fei Li at Stanford put together a team, and that team labeled lots of images. And so they had millions of labeled images. And that was one of the main breakthroughs. And then 2 very smart students of mine, one of whom you will see today, got a system working by using big neural nets on this big labeled data set, and they did a lot better than the best computer vision systems, and that caused a revolution in computer vision. The revolution should have happened sooner, because someone called Jan LeCun had been saying for years, these kinds of nets can do much better than you guys. But they could only do better with enough labeled training data. And they didn't have it till Fei-Fei Li put this data set together. That's not quite true. Jan submitted papers where his network did better than the state of the art, and they were rejected by conferences, even though they admitted they did better than the state of the art, because it was a neural network, so it wouldn't teach you anything. You wouldn't be able to hand design the system based on what the neural network did, because it just learned a big bunch of numbers. So that was of no interest to computer vision. Then over a period of about a year, they completely changed their mind. And this was the beginning of the downfall of conventional computer vision. There was this competition in 2012. All the computer vision systems we're getting more than 25% errors. And the net we developed at the University of Toronto by people who weren't really doing computer vision got 16% errors. That was a huge win, much bigger than the win we got on speech recognition. And people saw that, and they finally read the writing on the wall. I think they couldn't read the writing on the wall before because they weren't using neural nets. Now, the error rate is down to 5%. In fact, this slide is a few days old. It's now 4%. So it's amazing the progress there's been. And these are the kinds of images you can recognize. You don't have to have the whole object. It knows that's a cheetah. And its second best guesses is a leopard or a snow leopard. So its other guesses are good guesses. If you show that, even though the bullet train is only a small fraction of the image, it knows about what people tend to focus on in photographs. And so it knows that's a bullet train. And its other bets are quite good bets. For this one, its first bet is a hand glass. Sorry, its first bet is scissors. And its second bet is a hand glass. And its third bet is a frying pan. If you screw your eyes up, you can see why it thought it might be a frying pan. It didn't recognize that that chain is actually not a solid handle. So basically, this system needs glasses. But you can see that they're visually similar things it's getting. And the last thing I'm going to talk about is recurrent neural networks, which are really just feed-forward neural networks in time. I'm not going to talk about the technical details required to make these work really well. You can read a paper by Hochreiter and Schmidhuber in 1997. If you can understand that paper, you're better than anybody in machine learning was. It took 10 years before people understood what they were talking about. Okay, a recurrent neural network works like this. You have inputs, like images, for example, but they arrive over time. So this would be for video, let's say. And then the hidden neurons connect to themselves. So the connections that you see with the little green and red dots are connections of hidden neurons to themselves, and they're the same at every time slice, because it's the same way it's being reused. And then at each time slice it can give outputs. You might wait for a while before you give any outputs. And we can train that with the same backpropagation algorithm. And those also we couldn't get to work well in the 80s, but more recently using Hochreiter and Schmidhuber's version, people have been able to get them to work nicely. And then, Ilyas Skiva and Oriel Vinyals and Kwok Lee had a very good idea. Joshua Benjo also had a similar idea. But I think they made it work on whole sentences first. The idea is a really dumb way to do machine translation. We're going to do machine translation not by learning which phrases in English go to which phrases in French, which is how Google Translate does it. We're going to do machine translation by listening to the first sentence, understanding what it means, and then saying it again in the other language. That's the obvious way to do machine translation. The only drawback is you have to understand what the first sentence means. And we're going to get a recurrent neural net to do that. And it's really actually going to be fairly straightforward. So what we do is we have an encoder recurrent neural net that takes a sequence of English words. At each time step you put in one word. The word gets converted into a big vector of features. There's a big set of activations of features. These feature activations then drive the hidden units. And at the next time step, another word comes in. You get more feature activations. And the hidden units at the second time step are driven by the word at the second time step, plus whatever the hidden units were doing at the first time step. So in that hidden state, you're gradually accumulating information about what all the words were telling you, but in the context of what words already arrived, and you're trying to integrate that information into a single vector. By the time you get to the end of the sentence, you'll have some vector that's been influenced by all the words in the sentence, and we will declare that vector to be a thought. Now this seems very weird for people in AI, because people in AI and philosophy and logic always thought that thoughts were symbolic structures. They were sort of tree structures made of symbols or something like that. But we're going to say thoughts are just big vectors. And that's clearly what they are in your head. In your head, you hear some words, and then there's some state of activation of your neurons, and that's the thought you had. Okay, so we're going to take this thought vector, and we're going to say all we need to do now is turn that thought vector into words in another language. Of course, since we start off with all random weights, it'll be some random thought that's not related to the words to begin with. but after we've trained it, it will be. And so what do we do with the thought? Well, we make that thought vector be the input to a decoder neural net. Let's suppose it's speaking French. And the first thing the decoder net says is, what do I think the first word of this sentence should be? And it has bets about the various first words. If it's doing French, it might say le 40%, la 45%, cha 5%, and I don't know any more French, but there's some other words as well. So it'll make bets across the first word. If you were to pick one of those bets and then feed it in and tell it what word you picked there, that would then change its hidden state. It would have already said that. And it would then make bets for what the second word might be. So it's unlikely to think it's le or la if you said le first. It might think it was cha. Maybe there's 30% on cha now, and some more on other French words, and so on. So if you now pick from what it says and feed words in, it'll give you a sentence. And each time you pick, if you pick differently, it'll give you different sentences. When you're training it, what you want is that when it gives you a distribution across words, when it says the next word is probably cha, if the next word really is cha, you say, hey, that's good, change all the weights to make that a bit more probable. So go backwards in time, look at the pathway of weights that led to this decision, and go and change them all to make this decision a bit more probable. If cha was the wrong word in the given translation, you go back through that pathway and change all the weights to make this a bit less probable. And that's it. You just train it like that. It starts with random weights. You train it on lots of pairs of English and French sentences. And hey presto, trained on one pair of languages, it does comparable with the state of the art on a medium-sized database. And with more recent tricks that involve attention, it does even better. And once we've trained this on lots of pairs of languages, using the same thought vectors for many different languages, so you can take an English thought vector and translate it into many different languages with different decoders for those languages, we think we'll have something that's so good that you could, for example, take encoders for many different languages, you could take a decoder just for English, you could put it all on one chip and you could stick it in your ear. That would be the hope. I hope some of you have read The Hitchhiker's Guide to the Galaxy. Okay. So I'm going to finish by showing that you can put those two bits of work together. You can take the feed-forward neural network that recognizes objects and images, and you can feed the decoder network. Instead of feeding it with the thought that comes from an English sentence, you feed it with the thought or the percept that comes from looking at an image. So you look at the image, you do lots of clever early layers with clever tricks called convolutional neural nets, which I haven't explained. That just before you get to the class labels, you just declare the activity in that last layer to be a percept. And that's a percept that you know is looking at the image and understanding it in terms of the kinds of objects that might be there. And then you map that percept to a thought, and then you decode the thought into English, using exactly the same kind of network as you used for decoding an English sentence into French, except this is the English decoder. And if you show it that image I showed you at the beginning, it will say something like a close-up of a small child holding a stuffed animal, which is a pretty good caption. It's pretty impressive for something by pure learning to have got from the intensity values of pixels to a string of English words that's appropriate. Here's another example. If you show it that, it'll say a group of people shopping at an outdoor market. If you run it again, it might say something different. The thing that you probably can't read in the light type is the correct caption, which is better. It's people crouched around in an open market. But the point is, it works. Now, this will have big implications for document processing, because with this kind of technology, we can take a sentence and convert it into a vector that's the thought behind that sentence. And if you ask what a document is, it's just a sequence of thoughts. Once you've got rid of the words, it's a sequence of thoughts. And all we have to do now is model that sequence, and we've understood documents. What's more, we've understood how people reason. We've understood natural reasoning, which is what symbolic AI could never do. They tried all sorts of fancy screw-ups of logic to try and understand natural reasoning. But actually, this is the way to understand it. Now, you might not want to understand natural reasoning, because this will be reasoning on the web, and you can't really call it reasoning. But at least you'll understand what happens when people go through a document. I have some reservations about how long it's going to be before we can really understand documents like this. And my reservations are mainly to do with how many weights we have in a brain and how many we have in these networks. In these networks, we have typically 1 billion or less of these learned parameters. In our brain, we have about 100,000 times more parameters. And it may be you need that scale of parameters to get human-level understanding. We just don't know. So I'm going to show you a test for whether we've really got close to human levels. And this is a test that these automatic translation systems cannot solve at present. It's a test designed by the good old-fashioned AI people who had to find something these neural nets couldn't do. They were getting desperate. And so they found something the neural nets couldn't do. And once the neural nets have done that, they have to give up because they chose the battleground. They said, if you can do this, we give up, essentially. And you'll know that we finally won when we can do this, but it may be a few years off. And so here's the final test. If I give you the sentence, the trophy would not fit into the suitcase because it was too big, and you ask, what does that it refer to? You know that it refers to the trophy. And you know that because big things don't fit in small things. But if I say the trophy would not fit into the suitcase because it was too small, you know the it refers to the suitcase. Okay? You do that effortlessly. You don't realize you're doing this reasoning, but you just know the way things work in the world, and you can't put bigger things inside smaller things unless you're watching Doctor Who. So the question is, do the neural net translators, do they understand this? And the point is, they don't do better than chance. And it's very easy to test this because you just translate these English sentences into French. And in French, you're not allowed to say it. You have to say either le or la. And in the first case, it's either le or la, and in the second case, it's the other one. Okay, that's the end.
So, one question, how do you scale up today's neural networks to get to the scale at which you're saying perhaps you're on parallel with what we have?
Okay, I think it's going to be a large amount to do with hardware. Just computers getting faster is going to help a lot. That's why we're where we are. We're where we are today because of GPUs. That's what made the revolution. So I think hardware's going to have a lot. We have to hope that Moore's law will hold for another 15 years, depending on whether you hope that AI will happen. It's just possible, although I think extremely unlikely, that quantum computing will eventually work. That might do it. But I suspect for these problems, quantum computing won't be much help. Or we might get better algorithms. But I think it's a question of better algorithms and better hardware, and it'll take time. But we don't know whether you really need 10 to the 14 synapses to have human-level understanding. Maybe you can do it with 10 to the 9, in which case we might get there quite soon.
And final question before we move on to Russ's presentation. So if I have a whole set of thought vectors which are sentences about cats, is that functionally the same as what most people would call my concept of a cat when I think of one, in terms of what you can do with it as a technologist and the types of things you can build, or is there some essential difference?
I was a psychology student a long time ago, and they taught us about concepts, and I never knew what they meant. I never knew what the concept of a cat was. I know what it means when someone looks at a picture of a cat and says, that's a cat. And I know what it means when someone says, does a cat have whiskers, and you say yes. And if that's what you mean by the concept of a cat, these thought vectors and this perception system can do that. So that's good enough for me.
Marvellous.
Can I... Thanks. So my name is Russ, and I'm a student of Jeff. So excited to be here. So instead of making it a little bit more academic, I thought that I would just give you, 5-minute overview of what's been happening in the field and, the interesting things that I've been looking at. One of the exciting things that we see in the world today is the data, right? It's a lot of data from the web. If you look at the images, recommendation systems, social graphs, scientific data. And one interesting thing that's uniting all of these different areas is this sort of deep learning. It really brings together a lot of different areas. And if you look at the impact, right, the impact's been, remarkable. No, in the speech recognition, computer vision, as Jeff pointed out, his team really brought these two areas, basically turning them upside down. If you look at recommender systems, language understanding, more recently, places like drug discovery, medical image analysis are picking up in that field. And ultimately, what we want to do is we want to build AI, right? We want to be able to build systems that can see and recognize objects around us, that understand human speech, natural language understanding, and navigate around, and display human-like intelligence. And that will be happening in the next, 5 to 10 years. Here's one example of understanding images. A lot of us in the field are trying to work in that space. So how many of you know who that is? No? Great. This is Antonio Taraba. He's a prof at MIT. He's a computer vision professor at MIT. And so this is a picture I took of him at this year NIPS. And, you can tag it. It does reasonably well. But you can go beyond that. You can say, can you build a system that actually can describe in natural language what's going on in the image? And, you can look for nearest neighbor sentence. And the nearest neighbor sentence, by basically finding an image that's closest to the image that you've taken, basically says people taking pictures of a crazy person. But if you look at the model samples, the model generates, sentences like a crowd of people in a crowded area, a crowd of people walking and talking. It looks like a very reasonable understanding. If you look at the speech recognition, I like this graph. This is according to Microsoft's speech group. There's been a lot of development from 90s to about 2000, and then basically nothing was happening up until deep learning took over. So there's been a lot of progress in that area. In the space of recommender systems, companies like Netflix are using the technologies based on box machines and matrix factorization algorithms for improving their recommendation engine. If you look at deep learning for neuroimaging, there's a lot of different research happening in the space where people are trying to use that technology for understanding patterns that you see in the human brain. One other exciting thing in the last year, that was happening in the last year, is trying to tag images with sentences, not just with words of what you're seeing, but actually with sentences. So here are a few examples where given an image, you're trying to figure out what's the right sentence that can go with that image. Or you can go just tag the images, or given a word, can you find similar images, right? A lot of that technology is, again, based kinds of things that Jeff talked about based on deep learning, convolutional nets, and recurrent nets. You can also do interesting things. This is something that we've played at University of Toronto, where I show you an image. I take some concept out, like take an image, say minus day plus night, and you get images of castles at night. I particularly like the last two images. If you take kittens and you say minus ball plus box, you retrieve cats in the box. Or if you take a cat in the box and say minus box plus ball, you get cats in the ball. Right. So it sort of has some notion of trying to unify linguistic and images. Can you understand something about what's going on in the images? Caption generation, Jeff talked a little bit about it. In fact, there was a little competition between Google and Toronto. In fact, there was a competition between Google, Microsoft, Toronto, Berkeley, and Stanford. All of us were developing these systems at about the same time. And if you look at what these systems can do, it's remarkable. 5 years ago, somebody asked me, can you actually generate a caption and describe what's going on in the image in natural language? I would say, no way. But if you look at these images, a car is parked in the middle of nowhere. That's a pretty good description. There's a cat sitting on a shelf. It's a pretty good description. Here's some examples where the model is failing. It's always fun to look at. If you look at the first image, the model says the two birds are trying to be seen in the water. Right? So you can see the system is really trying, its best to. So there is a little bit of reasoning happening in these systems. These are not just systems that copy some sentences from the training set or from some corpus. It's really trying to be a little bit creative. Or look at the image with the bicycle. It says the handlebars are trying to ride a bike rack. Right? So, and that's again, the system is trying to reason what it's seeing in that image. So these are some failed cases. Go beyond that. This is a system where, given an image, you're trying to generate a short story about the image. So in this case, we trained the system on 7,000 romance books, romantic books. And the system knows about romances. And if you look at what it generates, we were barely able to catch the breeze on the beach and so forth. She was in love with him for the first time in months. She had no intentions of escaping and so forth. It goes on. And if you look at the last sentence, it generates the sun was just starting to fade away, leaving people scattered around in the Atlantic Ocean. So, there is some, obviously these systems are, to some extent they are primitive systems, but at the same time, it's trying to correlate what it sees in the image and what it knows about, romantic books. This is another example. Some people were talking about language understanding. I think that's a very interesting area of research. So this is a system where it's based on recurrent networks where given two sentences, you're trying to say, are they similar sentences? Are they the same sentence? If you look at the first sentence, a man is driving a car, his car is being driven by the man, you're predicting quite high score that they're the same, so the system gets it. Or a little girl is looking at a woman in costume, a little girl in costume looks like a woman, it's the same sentence. And the last example is an example where, these systems are failing. This is our system. A person is performing tricks on a motorcycle, and the performer is tricking a person on a motorcycle, right? So you can see that, the system is not quite right. Finally, just on the last thing that I want to point out is there's been some work on trying to recognize and try to go beyond learning from lots and lots of labeled examples. So this is an example of, can you actually do learning from one example? So if I show you this particular character, can you find me other characters like this? And people are very good at doing that. Machines are not. Or if I show you a new concept, can you learn something about that concept very quickly? And again, people are very good at doing that. Here's an example of where we showed a particular character to a person, to a human, and we asked the human to draw this character. Right? And humans are very good at doing it. Humans are very creative. And so we compared human drawers with machine. Right? So we build a machine that can draw these characters based on one example. And the question for you is that, can you tell me which one is which? Can you tell me which box is an example generated by a machine versus which box is an example generated by a human? Any guesses? So if we look at the first one, do you think the first one is the machine generated or human generated?
For risk of embarrassing myself, I'll say perhaps a machine. Does anyone else have opinions? A few.
The first one is machine, yeah. So how about if we go to the second one, the second character? Is the first was generated by machine? Maybe? No? So this is an example called Turing test, right? So we're asking people to ask, to say, is this thing was generated by a machine or by a human? And in fact, the truth is I don't know the right answer. In fact, it was actually in our paper, but I don't remember which one is which. Nonetheless, and that actually got a little bit of it actually got a little bit of press, so that's kind of it's kind of nice. There was a little bit of press about the work, about trying to actually build machines that can not just recognize, but it can also be a little bit creative and generate new examples and new characters. And in particular, like that particular title, say hello to our robots overload machines that can learn like people. And ultimately, I think that if we are going to be building systems that can take all these multiple modalities into account, images, text, videos, speech, and can integrate all of these things together so that we can build intelligent machines, so developing systems that come closer to human-like intelligence. And let me stop here. Thank you.
So, in keeping with the Star Wars theme, as it was mentioned earlier, if I bring one of your one-shot classifiers to the latest Star Wars film and a new character is introduced on stage, how do you develop a system that once that character has been introduced as like Mr. Zark, can now generalize and understand Zark whenever he appears? And what's the barrier?
Yeah, I think that it's an open question, but I think it's a very important question because people are very good at learning new things very quickly. The first time I've shown a cell phone to my kid, the kid understands that it's a cell phone. Right now, if we want to build systems that can recognize cell phones, I have to show you a cell phone in this position, and different backgrounds, different lighting conditions. I have to show you different colors and so forth before the machine actually understands that this is the cell phone. So how do we build systems that can sort of go beyond that is a really, really challenging task. And it will have huge implications in cases like speech recognition. First time you hear the word, Chewbacca, right? Like, what is Chewbacca? and you sort of associate Chewbacca to a particular character, and that's it. And you know what Chewbacca is. A lot of existing speech recognition systems are suffering from the problem of dealing with rare words. And sort of going beyond that is a challenging task.
And so, earlier in the day we heard from Richard Socha, whose startup has, he claims, an excellent food classifier. How can Richard combine his food classifier with the other classifiers he's trained so that they can collectively have a huge amount of understanding and do that efficiently? And today, is that just a very expensive process, and how do we get there?
Yeah, that's a good question. I think that in Rich's case, these guys are machine learning guys. I think they know about so-called transfer learning, which is you're trying to basically learn everything you can about the world, right? And especially you can learn, as much as you can about different food items, so that next time you see a new food item, you can basically recognize just from one example, oh, that kind of looks like something that we've seen before. Kind of looks like a funny mushroom, and this kind of looks like a funny apple, right? And maybe it's just a combination of these two that you put together to make a new food item, right? And but again, how exactly you can do it is really, really challenging.
Okay, great. We'll be taking a few short questions at the end, but now we'll just have Ilya do his presentation as well.
All right, thank you very much for your attention. So the previous two presentations, they discussed a lot of the interesting and exciting applications that are going on right now. And in my presentation, I would like to discuss one particular research direction, which I think is promising and is exciting, and that is the learning of algorithms. So I want to spend just a little bit of time to explain to give another perspective on what makes deep neural networks special. And the thing that makes deep neural networks special are the following two qualities that take place simultaneously. The first quality that deep neural networks have is that they can express the right kind of extremely complicated functions that can solve the problems we want. So, for example, if you want to understand what's going on in images, you've got this really complicated function that maps your pixels to whatever is in the image, and your neural network needs to be able to express this function. If it cannot express this function, then you will not succeed, no matter how good your learning algorithm is. The second property that you need is that your system can be learned from data. You need both. You need to be able to express the complicated function and learn it from data, and deep neural networks achieve both of them. Now, the reason deep neural networks are as good as they are is because deep neural networks are circuits. A neuron can easily implement a Boolean function. And this is why, if you have a deep enough neural network, it can basically simulate a computer for some number of steps. One limitation that current models have is that the data on which you test must be very similar to the data on which you train. And this is why currently, if you want to build an application, a lot of effort must be spent on collecting the good data. So, another thing which is key to neural networks is that they don't care what problem to solve. If you find a combination of a neural network and algorithm which achieves good results on one hard problem, it is very likely to achieve results on many hard problems as well. So now I want to just present to you work that I've been involved with that I'm personally quite excited about, which we call the neural GPU. And it's basically a kind of a neural network that can learn simple algorithms from examples. Now, what do we mean by simple algorithms? It means that the neural network, you can train it on, let's say, small examples of the problem and test it on large examples of the problem. So the kind of things that we've been able to do were to train it, for example, to multiply small numbers, and then you test it on the multiplication of large numbers. And this is a property that normal neural networks do not have. And by virtue of having this being quite similar to, by being essentially a conventional neural network but with a slightly repetitive structure, the model can train it on a lot more data as well, on large data sets, and we expect that this model will be able to achieve better results than other models on other difficult tasks. And this was work that was done with Lukas Kaiser. And I want to finish by mentioning my OpenAI, which is the organization I'm going to be involved with next. And it is a well-funded nonprofit with a strong mission, and our goal is to do the best research in AI that we can, and we want to be an additive force to the community, and we intend to collaborate with other research groups and universities. Thank you much for your attention.
So you say a neural GPU can learn to solve basic things like multiplication and addition. What is the most advanced thing you think it is capable of solving eventually?
So I should say that this model is not the final. It's not the final or the ultimate model. I think it's more. You should think of it as of a step towards models that can learn those really complicated. So, like, if you think of something like learning to add, how do you know that you truly learn to add? That you expect to be able to never make mistakes ever. Once you understand what it means to count and to add, then you just should be able to add any two numbers or multiply any two numbers. And you'll be able to achieve it for these kind of simple tasks. What is more exciting on the practical side is that this model is scalable. And so if you give it conventional data, we expect and hope, and we will soon in fact find out how well it works on real problems.
Just when you say real problems, what would a real problem be that you'd imagine you'd be able to apply this to?
So, for example, translation. So, in his talk, in his presentation, Jeff alluded to the difficulty of current translation models to achieve a certain level of understanding. Well, what we hope is that with these kind of models, because of their much better generalization abilities, they should be able to generalize to achieve much better results with the same amount of data. That's the hope, and that's the goal.
Great. And just one more general question for the panel, and then we'll try and take questions from the audience. If Jeff is still here in the background and could return, that would be fantastic. But for Russ and Ilya and Jeff, what do you think are the greatest challenges in the field right now which good work is being done on? And what do you think are the greatest challenges in the field right now that very little work is being done on?
I think the greatest challenge in the field is to use deep learning to make the real estate market efficient. That is, what you need to do is do an Uber-like job but on the real estate market and get rid of the parasites who take 5% of the value of your house every time you sell it. And if you think the taxi drivers made trouble, imagine what trouble the realtors are going to make.
I think that, I agree with Jeff, but I think that there are a lot of challenges that we face in machine learning. I mean, one big challenge a lot of us are trying to do in deep learning is unsupervised learning, right? Trying to figure out how we can make use of large volumes of unlabeled data. You can go on YouTube and you can download thousands of hours of YouTube video. Can you learn something about the world by watching videos? Natural language understanding is another big area. And again, Jeff alluded to that. How do you learn the meaning of sentences so that you can do better translation, can write stories? Ultimately, we want to build a machine that can write books. In fact, there are a few projects happening where you have a machine that looks at the movie and reads a book, or reads a book and generates a movie. And the final frontier is how we can actually build systems that can reason and make use of memory and reasoning. That's something that's, again, if you went to the NIPS conference that was taking place in Montreal just 3 days ago, these questions were popping up as the major questions of interest in our community. And one final thing, there's also a lot of exciting things happening in reinforcement learning, deep reinforcement learning. How can you build systems that can go from perception to actions? Ultimately, that's probably going to be the ultimate goal if you want to build a robot that navigates around and does interesting things.
And reinforcement learning is one of the techniques used by Google's DeepMind subsidiary to create the computer program that could learn to play Atari games. So it has a much greater promise of utility in the future than an old console, we are assured.
So Russ's answer was so good, I find it very difficult to add something. So, I mean, what's happening right now is that the field is growing so fast, and so many people are working on every conceivable combination of questions and techniques that you can think of, that it's really kind of hard to see what would be an important problem that people should be working on but aren't. In fact, if you can figure this out, then you can make progress on that, and that's going to be hugely successful. Say that I feel like Russ really covered the whole spectrum of work that's been going on. I would say that the one thing that Russ didn't mention, which is really exciting, is the robotics work that's going on right now in Berkeley. They developed a new reinforcement learning algorithm that learns from very small amounts of data. So small, in fact, that you can train robots from very, very small amount of robotic experience. Now, to say which are the things that do not get enough attention yet, maybe some kind of a lifetime learning. That's something for which we haven't really, you can imagine a system which gradually builds up its knowledge over time. As it learns more and more and more, it becomes smarter and smarter. We haven't reached the point where there are problems that demand such systems, but that will probably change soon.
At the NIPS conference, another subject of discussion was whether the field is being somewhat overhyped at the moment. There's a huge amount of interest, and I realize I'm slightly complicit right now, so this is embarrassing. But I'd like to ask the panel, do you think there's any risk of hype, or do you think that this time is different to periods in the past?
History will tell. History told before in the 80s, and it was overhyped. This time, however, we have what we didn't have in the 80s, which is when you use your cell phone, it's using a neural net to recognize your speech, and it's using neural nets to recognize objects. So we have some sort of solid foundation against it all being just hype. Perhaps it's being overhyped when we come to things like machine translation. Maybe it'll be a long time before it gets really high-quality machine translation. We don't know. I suspect it won't be that long. I suspect in 5 years we'll have really good quality machine translation. So really, you only know about overhyping afterwards. But certainly, it's not all going to go away like it did in the 80s. The neural nets are here to stay. Inevitably, some people will overhype them a bit.
I agree with Jeff. I mean, there is probably just a little bit of overhype, but at the same time, one remarkable thing about these models is that they actually work, right? And, it's not just they could potentially work, or you're expecting them to work 5 years from now. No, they actually do work. And that's the reason why I believe a lot of companies, when I talk to various companies, Google, Facebook, Microsoft, these guys are not just investing in the future. They're investing in that field because it actually delivers and actually brings profit to them. So I think that these kinds of models are here to stay. We still have a lot of things that need to be done. And ultimately, will these models take us to the actual AI? I don't know, but there's nothing better than what we currently have. If you look at speech, if you look at computer vision, even people who were very pessimistic about these models, they're using these systems right now because there's nothing else, there's nothing better than that. And in competitive fields that demands empirical results, you have to use what works the best.
Let me say one more thing. I think neural nets in the 1980s were like quantum computing is now. A few people thought it was going to be really big and was going to solve everything, but it hadn't actually. Well, it factored 15, but 15 is not that hard to factor. Now, neural nets are really delivering. And maybe in 20 years' time, quantum computing will really deliver. We really have products that work, and that's why it's not just hype. Now, you could also ask the question, is it being underhyped?
I mean, again, it's very difficult to add anything to these two very complete answers.
Is it being underhyped?
So here's the thing. It could be overhyped, but it could also be underhyped, and the future will tell.
That's a good quantum. I believe we have time to take a few questions from the
I have
audience.
a question back here. We'll start here, and then we'll go up front.
Thank you. So I was very glad to see an example in Jeff's presentation of the hard inference problem, hard for neural networks inference problem, which is currently unsolved. But that is a fairly simple one. There are much harder inference problems which actually have practical importance. So I was wondering what the panelists' thoughts would be on learning, say, the ordering relation on reals. And I will explain why is this important. So if you want to, for instance, for the purposes of question answering, understand the sentences which compares numbers, like currency amounts, for example, right? You would like to learn a representation which actually appropriately encodes that semantics. Right? How would we go about such a thing?
So I feel like the specific question that you ask is one that current models do answer. I mean, in fact, there have been papers, which I happen to be an author on, which try to do exactly that. They design neural networks which try to answer questions where they have access to various operators which are able to decide if two numbers are equal and some other information, which makes it precisely possible to answer questions that have some quantitative aspect to them. And I should say this was work by Arvind Nilakatan and Kwok Lee as well.
Sorry, I'll come here and then there. Yeah.
Hi. I was half expecting Jürgen Schmidhuber to take the first question for me again, but yeah, only a few people get that. My name's Raghavan. I'm from Deep Learning, it's a startup. You mentioned, Russ, unsupervised learning and reinforcement learning, and Ilya, you mentioned lifetime learning. And it got me thinking about the whole of humanity. We didn't have a labeled data set. So you can kind of think of us as being like an unsupervised learning model or reinforcement learning model. And I'm wondering, do you think unsupervised learning and reinforcement learning will reach the level of supervised learning as it is now? And what do you think will it take to get to that level?
So I've spent most of the last 42 years trying to get unsupervised learning to work well. I completely agree with you. People don't have a lot of label data unless you think that what happens next acts as a label for the past. And I think what it's going to take is new ideas. There's a lot of ideas we haven't had yet. Just doing stochastic gradient descent on feed-forward neural networks or recurrent networks isn't going to solve everything. And it's clear that most of the learning they do is unsupervised. We'll know it when we see it, but we're not there yet.
Hi. You guys have given us a lot of forward thinking on machine learning and how it will have a positive impact to humanity. I'm curious to hear about the other side. What negative implications can machine learning and AI have on things like the human labor force as they become replaced by these simple tasks by machines? And we heard last time I was here at Rotman, the trucking industry could be easily replaced over the next decade with self-driving cars. What happens to these displaced workers?
I think we have a real expert talking about that at 4 o'clock, so I'll defer to him.
Please take the microphone.
100,000 years of human existence to come up with an algorithm like yours. How long will it take, you think, a machine to come up with a new way of learning that will be very different than the way you have come up with this?
I've no idea.
This question is for Russ. I'm Brendan Calder. I'm with the Rotman School. I see here in your bio, PhD in computer science, University of Toronto, assistant professor, University of Toronto, but you're on the way to Carnegie Mellon. What would it take to keep you?
That's a difficult question. I think that I think University of Toronto is a fantastic school. It's got brightest minds. For me, the move to CMU was kind of a personal move because my wife also got a position at statistics department there. So both of us are moving there. And then, one of the other things that CMU has done that I think that other schools haven't is that they have their own machine learning department. It's the only university in the world that has a machine learning department. So you have over 100 PhD students that are doing machine learning. And that's a huge powerhouse for in that space. And I think that I would really love for University of Toronto and Canada in general to move in that field and create more academic positions at places like McGill, University of Toronto, University of British Columbia, and such, to keep up with what's been happening south of the border.
We have one final question.
Hi, Cameron Schuler from the Alberta Innovate Centre for Machine Learning. If you take a look at a space where you can't have a black box, like a regulated environment, aircraft controls, medical devices, is deep learning at a point where you could actually have the causality, if you use that as a technology in those spaces, where you could actually explain input versus the output and how you get there?
So there's something interesting about people, which is people claim they can explain why they do things, but they're typically wrong. They're just making up a story. It's like they've got a press secretary who doesn't really know what's going on. And I don't see why neural nets shouldn't be able to at least compete with that. If we can cut...
All right, a big hand for our panelists, please. Thank you.